Okay, it's 4:15, so we'll go ahead and get started. My name's Nate Slater. I'm an AWS Solutions Architect. And today we're going to be talking about Amazon DynamoDB for big data. And unlike many of the presentations you probably sat through today, we're actually going to take a hands-on look at this. So I'll be doing some live demonstrations of Amazon DynamoDB. And hopefully I will not regret the decision to do a live demo at this session. OK, so today we're going to focus on the how and not the what. A lot of the sessions that we present here, which have a lot of great content, tend to focus on what you can do with AWS, what customers have done with AWS. Today we're actually going to focus on how you do things with AWS. We're also going to learn how AWS services abstract some of the complexity of processing big data without having to sacrifice power or scale or even in some cases control. And then we're going to also demonstrate how combinations of services from the AWS data ecosystem can be used to create feature-rich systems for analyzing data. It's kind of a mouthful, but basically what that means is that systems like Amazon DynamoDB rarely live in isolation, right? They're most powerful when you combine them with other AWS services, and we're going to go through several scenarios today. So let's first just start by asking a simple question. What is big data? And like many technology catchphrases, this is kind of a loaded question, right? Depending on who you ask, you might get a different answer. But here at Amazon, we generally think of it across two sort of dimensions or characteristics. Big data obviously has size, but it also has velocity, right? It's not so much only the size of the data you're dealing with, it's also how fast that data set is growing. So quantity of data is increasing at a rapid rate. We're starting to see more and more that raw data from all kinds of different sources are being used to answer key business questions. Log files, that's probably the most mature sort of scenario for big data processing. By processing all this log data that your applications are generating, your web log data, you can get quite a bit of good information about who's using your application and how they're using them. Application performance monitoring, another area that's become increasingly important over the last several years as apps have moved from the desktop to mobile devices to tablets. You basically have all of this information that you can look at to determine how well is my app performing. What kind of experience is a user on an iPad on a cellular network getting versus someone who's attached to a desktop at their office. You also have application metrics, right? You can do things like A/B testing, right? You can roll out subsets of features and then compare the response that you see users giving to those new features to determine whether or not it's something you want to move forward with. And then security, obviously, very, very important, right? As you aggregate all this data, oftentimes you can look through it and do some pattern detection, pattern recognition to see, hey, are we seeing patterns of access that may represent a threat? So this growth of data means that the flow of data is moving at an ever faster rate. So megabytes per second is pretty normal with big data, right? If you're familiar with our Kinesis service, the write throughput to a single shard on a stream is 1 megabyte per second. So that's sort of just like where you start, right? And gigabytes per second are becoming increasingly common, right? And part of the reason for this is that the number of connected users is growing at an amazing rate. There are some estimates out there today that estimate there'll be 75 billion connected devices by 2020, and that includes not only the devices we know about today, phones, computers, laptops, but also things like smart devices, right? Internet of Things type devices. And when you're dealing with that kind of scale, 10 to the fifth, 10 to the sixth transactions per second are not uncommon at all, right? You need to be able to support 100,000, 1 million transactions per second. So, this diagram is showing here, where I feel at least that DynamoDB really hits the sweet spot of big data because it can handle both size and velocity. And on top of that, it also has a very useful structure. At its core, it's a key value store. But you can store complex types in it as well, such as JSON documents. And so it really is unique, I think, in the big data NoSQL solution ecosystem in that it can handle both size and velocity, right? It's not like something like a memory cache, which is really, really good at velocity, but not as good at size, right? You're not going to put gigabytes of data into RAM, at least not today. So transactional data processing is where Dynamo really shines. It can handle high concurrency. It does have strong consistency. You can specify the consistency level that you want when you're getting reads of data from Dynamo. It supports atomic updates of single items. So if you're changing a single item in a table, you can do that atomically. You can use conditional updates to dedupe your data and for optimistic concurrency, right? You can update only if a value hasn't changed since the last time you read the data. As I previously mentioned, you can do both key value and JSON document schemas. And it is capable of large table sizes. I mean, I know a lot of folks probably don't think of Dynamo as being capable of really large tables, but it can, right? The way Dynamo partitions data, you can go out to terabytes of size. I mean, that's a pretty big table. It may not be the most cost-effective way to store that data, and we can talk about some of those use cases later, but it will support it. OK, so let's jump in to our demos now and hope they work. So the first demo we're going to look at is going to use S3 notifications, which are a feature of S3 that generate events when certain things happen in your S3 bucket. And we're going to process those events from S3 with a Lambda function. The Lambda function is going to store some data into DynamoDB. And then we're going to have a second Lambda function that's going to read off the DynamoDB stream that's attached to the table that we're updating. And the data from that DynamoDB stream that's being processed by the Lambda function is going to get passed into an Elasticsearch instance. So in this case, what we're doing is we're basically storing raw data in Dynamo and then making it searchable with Elasticsearch. And so the use case here may be something, we have a large number of digital audio files in S3, right? Maybe we're building a streaming media service, and we want to be able to make those files searchable by all the things that people like to search for when they're searching for music, right? The artist, the album, the title, the genre. And we're going to use DynamoDB as the primary data store for all that metadata, and then we'll be able to do queries and indexing using Elasticsearch. So why are we putting data in two places, right? That seems a little odd. Well, Elasticsearch really isn't designed with the same availability and durability as Dynamo, right? So we want to use Dynamo as the primary data store, and Elasticsearch is going to be used to provide a very rich query capability on top of that data, much richer than what you can do with DynamoDB today using global secondary indexes and local secondary indexes. So how do we do this? Well, the first thing we're going to do is we're going to create a Lambda function that reads the metadata from the ID3 tag and inserts it into a Dynamo table. Then we're going to enable S3 notifications on the bucket storing the audio files. We're going to then enable streams on the Dynamo table. We'll create a second Lambda function that takes the metadata in DynamoDB that's being put into the stream and calls the index operation on Elasticsearch. And then finally, to wire this all together, we just have to enable that DynamoDB stream as the event source for that second Lambda function. OK, so let's jump right in here. So here I am in the Lambda console, and the first thing we're going to do is we're going to go ahead and we're going to create the Lambda function. I will zoom in as I'm doing this on the parts that are sort of the important parts. We're going to go ahead and skip this first step. We don't need to use a blueprint. So let's call our Lambda function something like process audio file. And the description will be read the ID3 tag data and insert into DDB. OK? We're going to use the Node.js runtime. And I'm going to go ahead and upload this from S3. I've already staged my Lambda function there. And let's do make sure I spelled it properly here. I can zoom in on this for you. So I'm specifying the S3 bucket, and I'm specifying the key of the zip file that contains not only my Lambda Node.js code, but also all of the dependencies, right? When you're deploying a Lambda function that has npm node module dependencies, you have to package it up as a zip file. I'll go ahead down here. This is just the name of the JavaScript file that contains the method we're going to execute. Let me go ahead and zoom out so I can see I'm going to go ahead and select the role. I've pre-created the role we're going to use here. So Lambda basically operates in the same way as EC2 does when you assign an EC2 instance to an instance profile, right? You put the instance in an instance profile. The profile is associated with an IAM role, and that role defines what that instance can do, right? All the other AWS API calls that it can make. Lambda is the exact same way, right? So we're going to need to do a get object from S3, and we're going to need to do a put item into DynamoDB. So this role allows the Lambda function to do that. The bottom part of the screen here, I'm going to bump up the memory a little bit. The ID3 tag reader does use a little bit of memory. I'm going to make the timeout 30 seconds. That doesn't mean this is going to take 30 seconds to run. It just means I don't want Lambda to time out my function until after 30 seconds has elapsed. We are going to be downloading files from S3 in the Lambda function. It's not going to take 30 seconds, but we want to have enough time for it to execute. So I go ahead and I hit save. This is basically what we're looking at here. We've got a process audio file function. It's running Node.js. Pretty much just a summarization of what we just did. Let's go ahead and create it. OK, great. So our function has been created. And now we want to test this, right? Before we actually start wiring in the S3 notifications, it's useful to test our function to see if it's working. So one of the nice features of Lambda is you can configure these sample events. And this is basically the JSON format that the S3 notification uses. And you can see it has the name of the bucket and the name of the object, right? So when an object is put to S3, it generates this JSON and passes that into the Lambda function, right? So I can actually use this to test right here. I click submit. OK. And it looks like you can see the little green check mark down here. It says execution result succeeded. And you can see we even have some logging information down here. Let me zoom in. Right, you can see this is some log information that I emitted in the Lambda function as I was reading the ID3 tag data. So everything looks good there. So now, as a result of this, the end result is we want to have data in DynamoDB. So if I go over to DynamoDB console and I click on our audio file table, we should see this item in there. And lo and behold, we do. Right, so our test worked. So now it's time to actually make this go live with data that's being written to S3. Okay. So what do we need to do that? Well, let's first go over into S3 and set up the event notification. And so I have my bucket here. Let me just refresh the screen. And I'm going to go over here to the events section. And again, I'll zoom in once I start typing all the stuff in here. And I'm going to click add notification. And so first, we're going to give it a name. Let's call it put audio file event. Now we're going to specify the S3 actions that we want to trigger this event. And so in this case, I'm going to select object created all, which will basically trigger the event if we do an S3 post, a put, a copy, or a complete multi-part upload. I'm going to limit this to only fire when we have objects that are being created in the audio files folder, if you will, right? S3 doesn't really have folders. This is a prefix. So basically, any object that has this prefix will trigger this event. And then finally, I'm going to select our Lambda function that we created in the previous step. And let me zoom in a bit so you guys can see. So right through the console here, we've now set everything up that we need to wire our S3 notification to our Lambda function. I click Save. That looks good. We can double check this now if I go over to Lambda. And I go to my function process audio file right here, and I click event sources. We should now see our S3. I guess that's kind of hard to see, but basically you can see that our S3 bucket is now an event source to this. So let me now go ahead and run a couple of commands here. First thing I'm going to do is I'm going to log into an EC2 instance that has the audio files. Okay, And now I'm going to go ahead and I'm just going to use the AWS CLI here to just copy a bunch of audio files that are attached to an EBS volume, attached to this instance or stored in EBS volume to S3. And you can see I just ran it, and let's run another one for good measure here. OK, great. And you can see it did a multi-part upload by default. That's why I had to use the object created action in my S3 notification, because if you're uploading large files, obviously we don't want the event to fire until that multi-part upload complete action has triggered. And if we go back over now, let's first check DynamoDB. I'll scan my table. And you can see we have a whole lot more data in there. So it looks like our Lambda function worked. I'll go over to Lambda. One nice feature of Lambda is I can actually take a look at some of the CloudWatch metrics that show sort of useful information about Lambda, such as how many times it's been invoked, the average duration of each invocation, and you can actually view the logs. And if we go over here and we look at this guy right here, you can see this is the log output of the Lambda function. So in this case, we're invoking this Lambda function once for every object that we just put into S3. It doesn't bundle them together. But we'll see with DynamoDB streams, it can also process events in batches. Oops. OK, so we're reading the metadata in. It's going into DynamoDB. We now want to make that searchable via Elasticsearch. So we're going to do that with a second Lambda function. I've already created this one. It's called process audio file stream. The process for creating this was totally identical to what we just did, so I didn't want to consume time walking through it again. So this has already been created. So it's all ready to go. What we do need to do, though, is we need to make sure we have the stream set up on the DynamoDB table. And so if I go back over here to my Dynamo console and I click on my audio file table, you should see, if I click on the stream tab, that we do have one, this one on the top that says enabled. This is my active stream on this table. The only reason I have a bunch of disabled ones is because I've been testing this, and so I keep deleting the stream and re-adding it. DynamoDB streams are like Kinesis. They live for 24 hours, right? So I've got my stream. Oops. Let me now go back into Lambda. And if we go over here to this tab, you can see, sure enough, my stream is enabled as the event source for this Lambda function. And if we scroll out, you'll see even over here on the side, it may be a little bit difficult to see, it actually says last result OK. So I just uploaded a bunch of files, so this actually has already run. So let's go ahead and just do a couple more files here. Let's let it run. I have another. There we go. I'm going to just copy a whole bunch of files. And while that's running, we can go back over here, and we can look at monitoring. We can view our logs in CloudWatch. OK. And so this is what this event looks like. Let me zoom in. So this is the JSON format that the DynamoDB stream passes in. So it passes me in the key of the item. And then I'm doing something, the stream that I enabled is what's called a new image stream. So I'm only seeing the new data. I'm not seeing the record prior to the update. I'm only seeing what it looked like after the update. But you can enable a DynamoDB stream to show you both, right? You would have just two JSON blocks in there. One would be called old image. That was the pre-update state, and then one's called new image. That's the post-update state. I don't care about the pre-update state in this case. I only care about the new image. And so this is what's been passed into me. And so to do the Elasticsearch, you can see some debugging information. What I'm doing is I'm basically taking that new image JSON, turning it into a JSON document that's suitable for indexing in Elasticsearch, and then calling the Elasticsearch API. And Elasticsearch has a REST API, so it's very simple to call it from JavaScript. And we'll take a look at the code for these functions in a second. OK, so our functions appear to be executing properly, and I can even show you if I go over here and very quickly, let me actually quickly go back here. Let me just get an ID of one of these guys. This guy here, about. And I think if I just do something like curl local, elk. Yeah, a little hard to see. Hold on. Sort of JSON that comes back from Elasticsearch, but you can see this. I just fetched this indexed document from Elasticsearch, and you can see, lo and behold, it has all of the fields that we have grabbed from the metadata from the S3 file and stored in Dynamo. OK, so let's take a quick look at the source code for these functions. First one, this is the function that processes the object from S3, rather the event from S3. And you can see the real sort of stuff that happens here is we call S3 get object. I'll zoom in on this in a second. You can see, well, it's kind of hard to see if I go back up. Maybe we can, oops. So this first block here is S3 get object, right? All I'm doing is just getting the S3 object based on the key in the bucket that was passed into me. Second step is I do the ID3 read, which is not specific at all to AWS, so we'll skip that. And then finally, in this last function, this is where I take the metadata that was extracted and I insert it into Dynamo. And I'm using the DynamoDB document interface to do that. So I construct a JSON document, and then I just do a put item into Dynamo. So pretty straightforward, right? Not a lot of code. I think this entire thing is 130 lines of code. And quite a bit of this is actually just doing the waterfall, the async waterfall, because Node.js is asynchronous. I need to make sure I serialize all these operations. So there's a lot of sort of boilerplate stuff in here. So let's take a quick look now at the stream processing. This one is in some ways even simpler. I'm basically passed in a batch of those DynamoDB update stream JSON documents. And I just essentially convert that update stream JSON, which uses something called the DynamoDB line format. I convert it to just a plain old JavaScript object that I call audio file. I set a bunch of properties on that. And then down here, I call the index method on the Elasticsearch client. Elasticsearch has a nice Node.js SDK, so I'm using that here. And so that's it. That's basically the code to essentially build a searchable index of audio files. And again, this one is only 85 lines, so pretty straightforward. OK, so let's go back to our presentation. Key takeaways. Dynamo plus Elasticsearch, you get the durability, scalability, and high availability of Dynamo with the rich query capabilities of Elasticsearch, kind of a nice combination of two different data stores. And then Lambda functions are sort of the glue that makes this all work, right? You can basically have Lambda functions that respond to various different events and then take action when those events occur. And the beautiful thing about Lambda is you're not managing any compute infrastructure at all. For folks that have been building on AWS for a number of years, you could do this entire thing with SQS and EC2 instances that are sitting on the SQS queues and dequeuing tasks. But we don't have to run any EC2 at all for this, right? In fact, the only EC2 that I'm running on this is the Elasticsearch instance. And when I built this, the managed Elasticsearch that was just announced last week wasn't available. So I wouldn't even need to run any EC2 if I were doing this today. OK, demo number 2. So here we're going to look at how you can execute queries against multiple data sources using DynamoDB and Hive. So say, for example, you have a bunch of items in your Dynamo table, and then you have a bunch of other data that lives in text files, and you want to basically do an ETL-type operation that combines the two data. You can do this using Amazon Elastic Mapreduce and Hive. Hive, for those that aren't familiar, is a SQL-like language or framework that sits on top of Mapreduce. So it has a SQL-like syntax, and what it does is it compiles that down to actual Mapreduce jobs that run in your cluster. So we're building our streaming media service, and we've decided that the ID3 data is good, but we need a little bit more in here, right? We want to actually be able to do dynamic playlist generation based on sort of other characteristics of the audio files. And so there's this data set that we're hosting on S3 called the Million Song data set. And it's stored in text files. And we've got our ID3 data stored in DynamoDB. And the Million Song data set has a bunch of other metadata about audio, about songs, right? It has things like the tempo and the key. It's just some other things that you could use to maybe construct a playlist of songs that sound alike, right? And what we're going to do is we're going to use Amazon EMR with Hive to join these two things together in a query. So to implement this, what you would do is you'd spin up an Amazon EMR cluster. You would create an external Hive table using the DynamoDB storage handler. You'd create a second external Hive table using the Amazon S3 location for the text files that contain the Million Song data. And then you create a query that joins those two external tables together and writes the results back out to S3. And then, of course, you could very easily load those combined results back into Dynamo. OK, so let's jump into the demo. So for this one, I have already spun up the EMR cluster, just because it can take sometimes 5–10 minutes to bring up a cluster. I didn't want to consume that time during the demo, just waiting for it to come up. So I've already brought up the EMR cluster. It's very, very easy to bring up a cluster using the EMR console, and very, very easy to enable Hive. It's just an option that you pick when you bring up the cluster. So here's my cluster right here. And the first thing I'm going to do is I'm going to log into this. I think actually I can get it from right here. Yeah, so I'm going to log into the master node of my EMR cluster. Let me just go ahead and get rid of the tables if they're already there so I can walk you through creating them. Oops, that's not what I wanted to do. There we go. OK, great. So now we're back at the clean state. So first thing we're going to do is we need to define these two external tables that are going to contain both our DynamoDB data in one table and then the Million Song database table in the other. So let's look at the Hive syntax for doing that. This guy right here is the DynamoDB external table. Zoom in. So pretty straightforward, simple syntax. If you're used to writing DDL in SQL, we do a create table statement. We pass in the column names and the data types of the columns. In this case, the sort of specific thing we're doing here to enable this is we have to tell Hive how is this table stored, and we're using this DynamoDB storage handler class to do this. And then the table properties down here, this is telling Hive how to map the attributes of the items in the Dynamo table to the columns we defined up here. And it's pretty straightforward. I mean, I encourage you to read the documentation on this. There's some pretty good docs on this. But you can see, I have an audio_file_ID column, and I'm mapping that to an item attribute called audio file ID. It's pretty straightforward. So that's the audio file table. Then we look at the metadata table. This one's even easier, right? These Million Song database metadata files are CSV files that I created from the Million Song database. Million Song database is distributed in specific database file format, and I converted those to CSVs, basically. This is even simpler, right? Here we're basically just saying, this is our table. These are the columns of our table. We're dealing with a delimited text file that's delimited by a comma, so it's a CSV file. And here's the location in S3 where those files live. And one thing that's worth pointing out is what's really nice about this is if we look at these files in S3, it's actually more than one file, right? So what's really nice is I can build a table that is going to link to data that's spread across a whole bunch of files in S3. And there's all kinds of fancy things you can do to do group bys when you create the table so that you're aggregating data across these files. You can filter by name. We're just doing something really simple here and saying, hey, every CSV file in this prefix of metadata is going to go into the table. So let's go ahead now and create these tables. I do this by running Hive. Let's create the audio file table first. And you'll see as we go through this demo, Hive is not the fastest query engine, right? It's really good for sort of batch processing ETL operations. It's not necessarily something you would want to do real-time looks at your data. That being said, I will caveat all this by saying I basically am using the default out-of-the-box Hive settings. I haven't tried to tune it at all, so there probably are things you could do to make it faster. And now I'll run the script that creates the metadata table. Great. OK, we've got our two tables created. And remember, now what we're trying to do is we want to join the ID3 data that we have in our Dynamo table with the million-song database data that we have in our metadata table. And we do that with a query. And the query looks like this. A little bit different than what you would do with a normal SQL query, but not that much different. So the first thing we're going to do is we're going to create another external table to store the results of our query. And this is basically the inverse of what we just did with the table creation for the metadata table, right? In this case, I'm saying, create me a table, and we're going to be row format delimited by commas. Lines are going to be terminated by a new line character, and then put this table is going to live in this location in S3. So what's going to happen is instead of reading the data from S3 in this table, we're going to write data into the table and then store it out to S3. And then the second piece is where we do that, right? We're going to do an insert into our joined results table from this select statement. And this is exactly like SQL, right? All I'm doing is I am joining the DynamoDB data on the artist, the title, and the album, which are the shared fields between the Dynamo data and the million-song database data, and then basically storing those results in S3. So let's go ahead and run this query. And let's see here. This may take a couple of seconds here. So now you can see it's printing out some information. It's actually running the Mapreduce job. So we get a whole bunch of log information here. Doesn't have to do any reducing because we're not doing any group by queries in here. And now we're in the mapping phase. So you can see if you were doing this in practice, Hive is really great if you schedule these things and they run overnight or something, and you have your results in the morning. OK, great. So finished. Took about 32 seconds. Now if we go to S3, let's go ahead and refresh. Yep, you can see I have a results folder. I've got this sort of ugly named thing in here, but I'll go ahead and I'll download that. Oops. Oh, that'll work. And what is it, 51BB? OK, let's just go back here. If I do a that's it. And you can see now I have my, let me make it bigger. I have my joined results, right? I have the key, the audio file key that's in DynamoDB, and then I have all of the million song database extra data, and I could easily now just reload this in. Why do I only have 7 rows here? Well, remember, it's a million song database, and apparently there's not a whole lot of overlap between the songs I loaded in and the million song database, but you can imagine that there probably are databases that are a lot bigger than a million songs, and you could get this data for basically any song that you were offering out of your streaming media service. So there we have it, basically streaming media pipeline using DynamoDB, EMR, and Lambda, and S3. OK, let's go back to our presentation. OK, key takeaways. EMR is really, really, really convenient for spinning up Hadoop clusters and running frameworks like Hive on top of it. And the beautiful thing about even this particular use case is I could have torn this cluster down when I was done with it. I kept it up and running just because I want to make sure everything was working for this demo. But under normal circumstances, a lot of times what you'll do is you'll spin the cluster up, you'll run your job, you'll get your results, and you tear it down, right? You don't pay for using any more compute than you have to. And then the second point, Hive is actually a great tool for combining data from different data sources, right? We were able to take data in a DynamoDB table and join it to data that was living in text files, right? Hive really excels at that. It's a very nice tool for that, so definitely encourage you to look at it. OK, so let's move on to demo number 3. So we've sold our streaming media service. We got a $1 billion unicorn valuation, got a nice exit for yourself and your investors. You've got a $100 million or so burning a hole in your pocket. You want to move on to the next great thing. So you are going to create an Internet of Things company. And what we're going to do here is we're going to ingest sensor data using Amazon Kinesis. We're going to read that sensor data off the Kinesis stream using a Lambda function. Lambda function is going to do 2 things. It's actually going to be 2 different Lambda functions. Diagram's not quite accurate here, but one of them is going to write it to DynamoDB. The other is going to write it into Amazon S3 as a text file, and then we'll have a third Lambda function that's actually going to respond to those text files being deposited into S3, just like we did in the first demo, and it's going to actually ETL those into a Redshift data warehouse. So what we're doing here is we're building an IoT pipeline so that you can actually look at the real-time data from a dashboard that's, say, querying DynamoDB, and then have some more deep analysis that you can do using Redshift. This is basically what I just said. We've got a number of sensors. They're taking readings. We're going to use Kinesis to ingest those. Dynamo is great for the fast access piece. S3 is great for the raw data. That's kind of your backup, right? You can always get back to it if you need to. You can age it out to Glacier or to other storage categories. And then we can use Redshift to do our true analytical type queries on it. So how do we do this? We're going to create 2 Lambda functions to read data from the Dynamo, or from the Kinesis stream, rather. One of them is going to basically update Amazon DynamoDB, and the other is going to write data into Amazon S3. So it'll be 2 different Lambda functions, and we'll look at both of those. And then for the third part, which is getting it into Redshift, I'm actually using an open source Lambda project called the AWS Lambda Redshift Loader. It's on the AWS Labs GitHub repo. And we're not going to look at the code for that today because this is open sourced already and you can look at it. It's a really, really nice tool. I'll walk you through how it works. That's what will actually get the data from S3 into Redshift. OK, so let's jump into this one. So first thing, oops. The first thing we'll do here is let's just go quickly over to the console. Just as I did with the EMR cluster, I've already created the Redshift cluster in advance. Again, I just didn't want to have you guys sit around and wait as this got provisioned. And provisioning a Redshift cluster can take a little bit of time. But you can see I've got a 3-node Redshift cluster. It's up and running here. So let's take a look at the actual data warehouse that we're going to be dealing with on this cluster. And I can show you the tables. It's a real simple star schema. It's this one right here. So we have a fact table. It's going to have the sensor ID, the reading, the date that the reading was taken from the sensor, and in this case, we're reading temperature off the sensor. This piece down here is basically something specific to Redshift. This tells Redshift how to distribute the data across the nodes. So like many distributed systems, like most distributed systems for that matter, Redshift wants to have data be uniformly distributed across all the nodes in the cluster, right? If the data is not uniformly distributed, when you do queries, you have to essentially copy data from one node to another, and that's inefficient. So we're going to say, let's use the sensor ID as the key for how we distribute data across the nodes in the cluster. Very, very similar to the hash key concept with DynamoDB. And sensor ID is a good one because presumably we're going to have about the same number of readings per sensor, and it's also essentially random. It's a 4-character hex ID. Then we create our dimension table, the sensor itself, and you can see we have the sensor ID, we have the geo-coordinates of the sensor, so that's where it's actually located. In this case, we're going to be simulating temperature sensors that have been spread out across the western United States. We have the city that the sensor's in, we have the state that the sensor's in, and the region. So this is a very sort of classic hierarchical dimension, right? You can see, just looking at this, oh yeah, you'll be able to answer some pretty nice questions. You'll be able to roll up to city, state, region, right? Very, very sort of classic OLAP type queries. And then we have the date time table here. And this is basically, again, a very sort of classic time table in OLAP where we break it out by minute, hour, day, month, and year, right? So the sensors are basically grabbing the raw date down to the second, but then we're also rolling up to these other portions of the time. So that's what our tables look like. I've already created these tables on our Redshift cluster, so let's actually go ahead and log in, or rather, just run a quick query here. I'll do it from this one. So Redshift uses the Postgres client libraries. So I have pSQL installed here. Oops. And what is it? Oh, wrong folder. There we go. Great, let me make it a little bigger. So these are all of our sensors. So basically you can see we've spread them out around the western part of the US. Okay, so those are already loaded. Now what we're going to do is I'm actually going to simulate these sensors taking temperature readings. And what I've done here is I've written a Python script that uses a publicly available API from forecast.io that actually, these are our real temperature readings. What I'm doing is I'm just doing a REST call. And it's going to, I think we have about 43 or 44 sensors, so it'll read these. Okay, great. So I've taken these readings and I've put them onto a Kinesis stream, right? So these data have been put to a Kinesis stream, and now if we take a look at Lambda, we can see Lambda reading data off that stream. And so let's take a look first at the one that's reading data off the stream and putting it into DynamoDB. Let's grab this. If I make it a little bigger, this is what the payload of the Kinesis data looks like. I have my sensor ID, I have my temperature, and I have my time. And so what we're doing is we're basically just reading this off the stream and inserting it into Dynamo. Time permitting, I'll show you the code for that. It's virtually identical to what we did with the demo one, right? You just do an insert into the Dynamo table. And we can even look at the Dynamo data. That's going into the sensor data table. And there it is, right? So the next function is the one that writes to S3. And you can see what it does is it's putting the data into a folder called sensor data as CSV files. And so what happens is these CSV files get written to S3. And just as we did with demo 1, there's a put object notification on this bucket. And that gets consumed by the open source, the AWS Redshift Lambda loader, right? And you can look at the code for that. But what that does is it's basically using Dynamo to track which files it's processed. And so you can see if I go into this processed files, it's keeping track of all of the files and the batches. It loads files in batches. And if we look here, we should have an open batch. Yes, and sure enough, we do. It's this guy right here. Right? And you can control the batch size through this loader. And in this case, I did a batch size of 2. So that means every time there are 2 files that have been processed and added to the batch, it'll actually then upload the batch into Redshift. So let me go ahead and run the sensor simulation again to get a second file. Okay. And all of this does happen pretty fast. Let's see if, yep, we now have no more open batches. So this has actually been loaded into Redshift. We can actually see this. If I come over here and go to the Loads tab, and I refresh this, it looks like it was probably this guy right here, yep, 5:01 p.m. And you can see the actual command it executed, this copy fact sensor data from this. This is a so when you load data into Redshift, you can load individual files or you can load groups of files that are listed in a manifest. And so we're using the manifest technique to load this. So you can see it loaded our data. And the final piece to all of this is let's actually run a query. And great, we got some data. I've been running this intermittently since September 24th, but you can see, today this is 10:08. Oh, I think we must be on a different time zone. You can see basically it's just doing a very straightforward aggregation where I'm counting and averaging these values. And you can see, because we're dealing with a dimensional model, I'm actually rolling up to state, right? So the sensors themselves are located at specific geocoordinates, but I can actually do an aggregate up to the state. And if we look, oops, over here, the query is real straightforward. I just join my dimensions to my fact table, rather, and then do a group by. And then order it so it looks good. And in real life, you probably wouldn't do this by hand. I'm a coder, so I like writing code, but most people would actually use like a BI tool to actually look at this data, maybe a pivot table, something like that. Okay, so that's it for the demos. Let's just finish off the presentation. So key takeaways, theme that we've been riffing on throughout this whole session. Kinesis, Lambda, DynamoDB, you get scale, durability, and availability with really, really low operational overhead, right? Again, no EC2 instances at all in this. Not that EC2 is bad. I love EC2, but it's just one other thing you need to worry about and run, right? In this particular case, we did put data both into Redshift and Dynamo, and I didn't really focus on the Dynamo part, but that would be if you wanted to do like a real-time dashboard or maybe a map that showed you your sensors, you would want to actually probably pull that data from Dynamo, right? Redshift doesn't like high concurrency, right? It has a limited number of active connections that you can have. So if you wanted to have like a mobile dashboard where you're going to have potentially thousands of mobile devices that are looking at the sensors on a map and seeing the last temperature reading, you'd want to use Dynamo for that. Redshift, though, of course, is better for the deeper analysis, right? You can build star schemas, you can do rich queries, join data together, do aggregates. It's very, very good at dealing with very large data sets, so you can go way back in time on these queries. And then Lambda, loading data into Redshift, I mean, you're basically doing ETL continuously, right? I wouldn't necessarily recommend trying to get this down to sub-minute ETLs. That's probably a little too frequent. And if you're going to play around with the AWS Lambda Redshift loader, you want to pick batch sizes that sort of are sane for doing ETL to Redshift. But certainly 5 to 10 minute increments is not a problem. And what that essentially means is that your data warehouse is now really only slightly eventually consistent. It's not that far behind the actual live Dynamo data. So a couple closing points. As we saw today, Dynamo is really versatile. You can use it in a lot of different ways, and it works really, really well when taken in the context of the larger data ecosystem. Most big data solutions really are going to use different tools, right? There aren't really that many use cases where you're going to use one tool and one tool only. So oftentimes you're going to use a combination of EMR or Hadoop, Kinesis. You might use Apache Spark for certain things, right? So you sort of have to consider this tool set in sort of the larger context. And AWS ecosystem has a very rich and powerful set of services to build these architectures, right? With Lambda and Kinesis, RDS if you're dealing with relational data, Redshift, EMR. You can run Spark on top of EMR. There were a whole bunch of announcements this morning at the keynote, like Firehose, for example. There's a BI service that's in preview now, right? So there's a lot of just sort of great services that you can combine to put together some pretty compelling big data architectures. So that's all I had. Hope you enjoyed it. It was pretty fun building it. I'm glad it worked. That would have been embarrassing had it not worked.